Hello, this is Mr. Mitchell. We're going to have a video on organizing and presenting data. In this case, I put organize for some reason. Oh well, it's not going to change the content. Uh, it's important to have a scientific mind, to be skeptical of coming to conclusions without much data, to ask questions, to be curious, and to do some kind of observation, maybe even experimentation. And it's important to be able to do that, but it's equally important to be able to organize and present the data. Now, line graphs are good for showing continuous changes, and here's an example. Here we have somebody whose weight gain is being measured over years in time. The time on the bottom, the weight gain off to the side. Time is the independent variable. An independent variable stands alone and is usually not changed by the other variables. This time is going to keep going on regardless of what John ends up doing with his weight. So this would be an independent variable. Often time is a good independent variable in a line graph. The dependent variable here is John's weight. Now you can see that that is what is changing over time, and the dependent variable is dependent upon other factors. What his weight gain has lots of things that it depends upon. Um, this is also kind of like a test score might be a dependent variable with different factors like how much sleep you got and how hungry you were when you took the test, maybe even where you were in the room when you took the test. There's something else called a controlled variable. Controlled variables are things that you, the experimenter, controls. You can't control the year, and you're just observing John's weight. But if you control, like, say, how many carbonated beverages John has throughout that year, or control how many carbohydrates he has throughout that year, that would be a controlled variable. And controlled variables are really important in determining something. If John's weight did go down by taking out something like carbohydrates or carbonated beverages, hey, John has learned something in that case. So line graphs usually show the independent variable on the x-axis and the dependent variable on the y-axis. A person who never saw this experiment that would have a controlled variable with John should be able to look at the graph and the chart and see what went on there. Let's talk about a bar graph now. At the top here is a bar graph. And I say at the top here, you can see my little cursor is spinning. Hopefully we will get to that soon. Oh, here it is. At the top here is a bar graph. A bar graph is useful in comparing two items. And you see here, you can actually extend the bar graph to compare more than two items. The independent variable is not as defined here, but I guess you might say that the number is the independent variable here. And the independent can go on the side or on the top. Here at the bottom we have a pie chart. If you have analyzed a compound, like in this case the composition of the Earth's atmosphere, and see what you have as to parts of the whole here. Parts of it are nitrogen, 78%, 21% is oxygen, kind of a familiar pie chart to you. And that's when you have parts of a whole, that's a good reason to have a pie chart. Let's take a look at something else here. In using scientific data, we sometimes need to express measurements using numbers that are very large or very small. Let me look back at something real quick. Oh, I should stay on this page because of these very large numbers right here. That's why I'm talking about scientific notation. Speed of light, for example, here is 300 million meters per second. I mean, that's just a staggering number right here. Oh, here it is. I'm finally getting this correct here. 300 million meters per second. If you want to calculate the time required for light to travel from, say, Neptune, you're going to be dividing a huge number by a huge number. And this is exactly what we're looking at here. The distance from here to Neptune in meters is, well, that's what, 4.6 trillion. So whenever you do have science, you sometimes have big figures or even small figures. So to reduce the number of zeros, mathematicians long ago came up with something called scientific notation. This is the number multiplied by the power of 10. And now we get to this. For example, the power of 10 here, 10 to the fourth, is going to be 1, 2, 3, 4 zeros past the decimal point. So 10 to the fourth is going to be 1 times 10 to the fourth. It's going to look something like, let me write this out somewhere here, stray mark, 1.0 times 10 to the fourth. 10 to the fourth is 10 with this decimal point being moved 4 times. My bad, not 10. It's 1 with this decimal point being moved 4 times. So 10 to the fourth is 1, 0, 0, 0, 0. The decimal point here is moved 4 places. So instead of having this big number, 10,000, you would have 1 times 10 to the fourth. And 10,000 is not that big a number, but when you get into the millions and the trillions, scientific notation definitely is a little bit less of a handful, especially when you multiply and add and divide and things such as that. So let's take this big number right here. We're going to see how we're going to make it 4.0 because you take the first number and then the one after that times 10 to the what power would it be? See, how far did you move the decimal point in getting to the 4? How many spaces are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 9, 10, 11. Looks like you've moved the decimal point 11 spaces. 1 times 10 to the 11th. Let me make sure this is right. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, so that would be in scientific notation 4.0 times 10 to the 11th. So what do you do with things like this? Very, very small numbers. Here's a very, very big number. What do you do with a very, very small number? Well, let's take a look right here. We have some very, very small numbers here. Oh, stray mark. But notice you have scientific notations, but it has a negative sign here. Let's see how that is done. You would still take the first digit that is not 0, put a decimal after it, and then you can include the digit with it. So 1.5 is what you're looking at. So 1.5 times 10 to the something. Let's see how long it would take to get from here to the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let me make sure that's right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is 1.5 times 10 to the 10th, not 10 to the 10th, 10 to the negative 10th. If it were 10 to the 10th, it would be a big number like this. See, the big numbers, the positive numbers, are going to be the big numbers. The negative numbers they're not going to be negative because they're going to be very small numbers. So very small numbers are scientifically notated with a negative exponent, and the very, very large numbers are scientifically notated with a positive exponent. So can we do the reverse? Can we go from scientific notation back to whatever the normal number is? Well, let's see. We have 4.9, and we're going to move that decimal place 5 spaces because since you have a positive exponent, it's going to be a large number. It's going to be less. It's going to be more than 1. Well, you know what I mean. So we 5 spaces. There is 1, and I believe if I put 4 zeros after it, I may have it right. Let's see. I'll put the 4 zeros. So we've got 1, 2, 3, 4, 5. That's exactly right. So that looks like it would be 490,000. So 490,000 written in scientific notation would be 4.9 times 10 to the 5th. Okay, what about this one? We have 6.8, but we have 6.8 times 10 to the negative fourth. Remember, negative will send the decimal back the other way. I never thought about it, but I wonder if you can think of it this way, the negative pointing in that direction. Well, either way, whether you remember it that way or not, the decimal will go this way. So 1, I think if I put 3 zeros here, 1, 2, 3, then I might have it. So I had 1, 2, 3, 4. Yes, the decimal point would go right there, and often you put a 0 before the decimal point. So that would be 0.00068. Written in scientific notation would be 6.8 times 10 to the negative fourth. So that's kind of what you're looking at there. Why don't we take a look at this? So what do you do when you multiply and divide these kinds of numbers? When you multiply two scientific notation values, you add the powers of 10. Add the powers of 10? Oh, then that makes this very easy, because you would multiply 6 times 4. 6 times 4 equals 24. And then you add 8 and 5. So that would be 24 times 10 to the 13th power. 8 plus 5 is 13. But what you would then need to do is make this 2.4, because scientific notation is where the decimal's right after the first one. So how do you make 24 times 10 to the 13 2.4? Well, that's simple. You just move the decimal one more spot. So it's 2.4 times 10 to the 14th. So what you do, you end up multiplying the digits and then adding the subscripts. Multiply digits, adding subscript. What do we do about this? So we have 9.0, should have put that there, times 10 to the 7th, and 3 divided by 3.0 times 10 to the 5th. When you divide, you subtract the powers of 10. And notice I had some easy numbers here to divide. So 9 divided by 3 is 3. 3 will go into 9 three times. So that would be 3.0 times, now what do you do with these? You subtract these. Oh, that'll be easy. Times 10 to the 2nd power. Now, wasn't that easier than getting those into bigger digits and then divide them? Much easier. And 3.0 times 10 to the 2nd power is going to be your answer there. And you can imagine that we are going to use some of this in class and give you some practice. Well, let's see what's next. Okay, when using measurements in calculations, the answer is only as precise as the least precise measurement used in calculation. If you're calculating the area of a rectangle with the measurements of 5.871 times the other side of 8.14, then what happens is punching in both numbers shows this. But you do not know the precision of this area to the nearest hundredths of a thousandths of a meter, which is exactly what this is. You don't know it that well because the least precise measurement was only to the hundredths. So to be more precise, you must round the value to the least precise calculations, and that's why you use significant figures. In this case, the answer should be to the nearest hundredth because the least precise calculations to the nearest hundredth. That's exactly why. What about with adding and subtracting? If you have 6.3421 seconds plus 12.1 seconds, you should have 8.4 instead of this big number because your least precise thing that you're adding is to the tenths. So that's exactly what you should do here. Your answer should be in the least precise value. And of course, you need to put the units with it. Hey, I hope you've learned a little bit about significant figures and scientific notation.